Okay, so let's go ahead and finish this, or let's get this started. This will be part 3 of our videos. You should have practiced this problem. We are going to look over this and talk about this in class. Like I said, now that we are going to start hitting more of our physics content material, I want to spend that time during class time going over those questions with you. Before I go any further, though, I need to kind of go back over a page or so and talk or tell you one more thing that was pretty important here. Let's see. I should have told you here, and I guess I didn't. Normally I wait till like unit 3 or 4 to kind of say this, but let me tell you now in unit 2. Vectors. We know that vector is something in physics that has magnitude and direction. The word magnitude means amount, a value, a number, and a direction. Like 22 meters per second north, 22 meters per second home, 22 meters per second towards moving backwards. That would also be considered a direction. Okay, but I should have also explained or said that vectors, they also are represented with an arrow. And here are some really good examples. We see how we talked about this already, the canoe. And we had the canoe were going against the water, and then the canoe were going with the water. And both of those were represented, or they were showing vectors, and they were represented by arrows. So a vector is represented or shown with an arrow. So I'm going to put right here, shown, or I should say, I don't know, the word represented would be a good word. Displayed, given. It's always in a form of an arrow and a form of an arrow. And let's go ahead and talk about that a little bit more as well. Yes, it is an arrow, but if you can see here, look at those arrows here and the arrow here. Look at the arrow here and the arrow here. Now, the difference between those arrows and between these arrows is, number one, yes, they have different numbers. But number 2, let's look. This is 2 and this is 1. The 2 arrow is larger by the 1 arrow. So a vector is in a form of an arrow. And let me go ahead and write it over here. The arrow size is due to the magnitude. Okay? So what I'm trying to say is the bigger value or amount, the bigger the arrow. All right? The arrow is also going to be pointed in the direction of that vector. So whether it's going right, left, up, down, northeast, southwest, okay, the arrow should be pointed in that direction. And when you do write a vector or draw a vector out with the vector arrow, you should always go ahead and give the magnitude, which is amount, and as well as the units that go along with it. When you draw the vector arrows, if you're drawing a 2 vector versus a 1 vector, your 2 vector better be double the size of a 1. Don't draw a 2 vector, like that and call this a 2. That's not going to cut it. That is not going to be okay. This might be a 10 or a 12, but it's definitely not going to count as a 2. Okay? So you can't oversize the vector. It needs to be proportional to what you're talking about. So I wanted to make sure I let everyone know that before I forgot. Let's go ahead and continue on this part 3 of the notes. Part 3, we're going to start talking about graphs. Distance versus time graphs, which are speed graphs. That's important to know. Now we call them, the shortcut is a DT graph. One more time. A DT graph is a speed graph. It tells me how fast my object's going. In a DT graph, time is always on the x-axis and the distance is always on the y-axis. Okay, dry mix. So because of that, let me go ahead and write that out. Dry mix. Then that means that distance that's on the y-axis is the dependent, and time, which is on the x-axis, is the independent. It's the manipulated. Okay. Here it is. This is a DT chart. And I'm going to go ahead and put DT chart. And here's my DT graph. Okay, they don't have it labeled, but they should. It's a DT graph. Now it says, let's look down here, and this is a DT graph, and this is a DT graph. Okay, now what's the difference between those two DT graphs? We can see this one over here goes up this way, and this one goes up like that. Okay, a lot of the math class and a lot of the stuff that you learn in math class is going to start carrying over here to physics. We're going to start using that math in real life situations. Okay, so we can see that here is one DT, here is the second DT. Looking at these two DT graphs, they are different. The difference between them, hopefully we see, is the slopes. So between here and here, these two DT graphs have different slopes. Right? Remember that slope from math class, rise over run? Okay? Same thing here. We're going to pull that rise over run that you've learned from math class over into physics. So it says here that both graphs show the same two variables, which is distance and time. But the line on the right is definitely much steeper than the one on the left. The difference tells you that the objects were moving with different speeds. So those different slopes are indicating how fast they're going. The steeper the slope, the line's steepness is called its slope. And remember, that's what we call rise over run. And in the distance or the DT graphs, that slope is going to tell you, for here for physics, distance over time. Rise over run. Distance over time, which is going to be equivalent to the speed. Again, one more time. A DT graph tells you the speed of that object. Okay? So let's go ahead and look at a few DT graphs. On class for Monday or Tuesday, we are going to do nothing but DT-VT graphs and worksheets, and I'm going to show you some shortcut methods on what I use so I can look at a DT graph or a VT graph and indicate what's going on quickly. All right, we don't want to take forever trying to figure it out. Next one over here, determine the average speed of the car in the following graph. Okay, well, to learn the speed or figure out the speed, we know that speed equals d over t, rise over run. Okay, let's look at the total distance first. The total distance is, we're going to see how high up it went. Here it is. We can see on the y-axis it's 300, and look at that, it even tells you in parentheses miles. It should always tell you the SI unit that goes along with it. So 300. Don't forget the shortcut for miles is MIL, not an M. The total time, come over here, look down, tells you it's 6. Let's look at the label on the x-axis. It says hours, so 6 hours. So our equation is going to be speed equals d over t. Our work, well, our distance is 300 miles. Our t is going to be 6 hours. You're going to find your answer in miles per hour, and you can shortcut it as mph for your miles per hour. Alrighty, turn the page. Alright, so here's some more DT graphs that we have and we want to look at, because there's going to be a lot of lines on these DT graphs, and it's going to be important for us to figure out what they mean. Let's look at the first one over here. Continuing looking at DT graphs. First thing, let's look at this DT graph. I'm going to call this one number 1, number 2, and number 3. I'm going to go ahead and just, here's my slope here. And actually there is no slope, right? This is a straight horizontal line. Here's my slope here. Remember last unit we talked about slopes that went upwards. We call those direct proportional. Okay, that's a direct relationship or proportionally direct relationship graph. But look at this slope on number 3. It goes downward. We also talked about that line that went downward. We call that an inverse proportional, directly inverse graph. Okay, on number 2, when one goes up, the other value goes up. On number 3, when one value goes up, the other value goes down. They are opposite. Okay, so let's look at the first one where there is actually no slope at all. So I'm going to see this because I know from math class a long time ago that when I see this line, there is no slope. Okay. The next one, I see that this line is moving upwards. I'm just going to put direct relationship. And this is an inverse. I don't know why I put a P at the end. Relationship. Okay, so that's just a little bit of information that I already know before coming into this set of notes. Now let's go ahead and look at the information that they want us to find down here, solve for, and then let's write down up here what is actually going on. So the first one for number 1, the distance. They would like to know the total distance. How far did this object travel? Look at that. Bam, there it is. 20. The next one, miles. Number 2, they would like to know what's the total distance here. It stopped over here. Let's go this way. Do we see that? 100 miles. And then they would like to know on number 3, what's the total distance? I'm going to come over here. Do we see that? 20 miles. All right, let's go back to number 1 again. They want to know the total time. I'm going to go ahead and go down to my x-axis. What's that? Let's see. It's about an 8 hours, give or take, 7.5-ish. Let's look at this one. It's about the same also, 8 hours. And then the next one, that's about, I'm going to go ahead, they all look like they're at the same at the 8-hour mark. What is the formula for average speed? So they're all going to have the same formula. Speed equals d over t. So I'm going to write that in. Now they're asking you to go ahead and show your work as well as give your answer with SI units. Let's go ahead and you complete this information over here. I'm going to highlight this over because I feel like we need to talk about this. I'm going to make sure that your math is good. Again, I don't get to see you, so I don't get to know exactly how your math skills are for everybody. It's a little tough for me to figure it out and learn it this way. But I'm going to leave some of these problems here available for you to answer, and then when we meet with each other on our Teams meeting, then we can go ahead and go through it. Again, when I'm calling on you, I'm not personally trying to pick on you. I don't even get to see you in class every day, okay, like traditionally. I'm picking on you, and I'm calling your name because we need to get through this information, okay? We need to see whether or not what you know and what you don't know. So be ready for me to call on you. Next one, it says over here, well, what's going on at this line, this line, this line, and this line? Well, I guess I should have told you over here a little bit more information at the top. This one, when you see there's no slope and it's just a horizontal line on a DT graph, and I want to make sure I say that, DT, because a VT is completely something different. Oops, sorry. A DT, when there is no slope, equals no slope equals no speed. Let's look at this one. When I have a direct relationship line, then that slope or that object here is moving away. And then when I have an inverse relationship line, that indicates that my object is moving back. It is moving away from the origin or away from home, away from the starting position. This one's moving back to home, back to the starting position. Okay, we'll come back to this math when we see each other on the meetings. So now let's go down here. Line number 1. Moving away. Flat line. No slope. We call it at rest. We're going to use that word a lot all school year. It is at rest. Next line. Oh, look, it's moving away, or it has an upward slope, so it's moving away again. And then the last one, it is an inverse relationship line that's moving down. And in this case, it is moving back. Not like it's moving backwards, but it's moving back towards the origin. Next part over here, circle the line where the object is moving the fastest and put a star on the line where the object is moving the least. All right, I'm going to highlight so that way we can discuss and talk about that one in our meeting. Let's keep going. We have 2 more little graphs down here. What's happening if the object speed isn't constant and changes over time? So let's go back up. You can see that those are nice, constant, straight lines on those graphs. Let's look at this one. No slope, a direct proportional graph that's completely nice and straight slope, a nice, straight, perfect slope. Well, let's look back down over here. Look at this line. It swoops up, and this one swoops towards down. It's like it's making a hill or something, a mountain. So, when we have a curve line on a DT graph, that indicates that there is a change in speed. Okay, so this curve and this curve indicates that there is a change in speed, meaning that it's speeding up or it's slowing down. It could be speeding up away from the origin or away from home, or it could be slowing down or speeding up, moving back towards the origin or back towards home. And we will talk about those curves in our teams meeting. Let's turn the page. Next part of our notes is acceleration. Now, most of us right now are probably just got our driver's license and we're driving, or we're in the midst of getting our driver's license, so we can start driving soon. But those driver's licenses are pretty important to us. And one of those words that you talk about in defensive driving or your online driving or at home driving is acceleration. So most of us in everyday world use the word as acceleration as speeding up, right? It's going to accelerate. It's going to speed up. But in physics, acceleration actually has a definition. Okay? So the definition for acceleration is defined as a change in velocity. Okay? A change in velocity is the physics definition for acceleration. Now, again, most of us kind of have that, oh, that means that I'm going to hit on the gas pedal and I'm going to accelerate or speed up. But in physics, it's not just hitting on the gas pedal, it's speeding up. Okay? Let's talk about it. It says here, look at the following data. Describe the object's motion. So let's look at this data chart over here. My object over here is at 0 seconds, 0 velocity. The time goes up by 1 second. It increased by 1. And then my time right here increased by 1. My time again increased by 1 second. Right? So my time is continuously changing or increasing by 1 second. Let's look at the velocity. From 0 to 10, what happened here? It increased by 10. From 10 to 20, it also increased by 10. From 20 to 30, there was another increase by 10, and it continues. Increase by 10, increase by 10. So now that we actually wrote down and analyzed what the graph is actually doing, yes, I see the numbers are changing over here, but how is it changing? As for every second that time is continually going, my velocity is changing by 10 and increasing every single second. Okay? So, what's going on is for every second, right, the velocity increases by 10. That's the information that we found. In the table to the right, the velocity is increasing, continuously increasing steadily by 10. And the definition for acceleration in physics is a change in velocity. Is the velocity changing? Yes, it is. Remember though, velocity is a change if the object's change in what? So let's stop for a moment. Let's go back to this word right here. Okay, now we talked about velocity and speed already, and we also talked about how velocity is a vector quantity. A vector is a quantity that has magnitude and direction. It's a vector. So if we're talking about velocity within the acceleration definition, right, then that means that if velocity is a vector, then acceleration must be a vector as well. Yes, it is. Now, what makes a vector a vector? A vector is a vector because of the direction that goes along with it. And so, remember, velocity can change if an object is changing direction. Okay? And because of that direction change, then that means that acceleration is changing. So acceleration occurs when an object is increasing the rate of change in velocity in a given time interval. Next one, I don't know why they have number 3. Oh, 1, 2, 3. It says here, constant acceleration occurs when an object changes its velocity by the same amount each second. And we saw that over here, constant acceleration. Don't confuse it with constant velocity. If an object is changing its velocity, whether by a constant amount or a varying amount, then it is accelerating. That object is accelerating. An object with a constant velocity is not accelerating. So let me shortcut this for you. There are 3 ways to change acceleration, or there are 3 ways to accelerate. Okay? So I'm going to put right here, acceleration. 3 ways. Number 1, speeding up. Oh, my whole camera fell down. Let's go back. Sorry about that. Oops, okay, I think I got it. So number 1, it's by speeding up. Right? Kind of like, when you're driving your car, you're hitting that gas pedal, you're going to accelerate, you're going to speed up. Now, another way to change acceleration, or for you to be considered to be accelerated in physics, is changing your velocity. not only can you speed up, but you can also do the opposite and you can slow down. Slowing down is also accelerating. I know it sounds opposite. Normally in everyday language, we would call it decelerating, right? Decelerating and accelerating are the same exact thing in physics. You're speeding up and you're slowing down. What are you doing? You're changing your velocity, which is accelerating. And because velocity is an important part of acceleration and velocity is a vector quantity, then that means that if you change direction, then you're accelerating. Now, what if you have, let's go back to over here where they're talking about, what if you have constant speed, meaning that you have cruise control in your car and you're cruising along at 42 miles an hour? Are you accelerating as you drive down 45 north continuously straight? No, you're not. And the reason why you're not accelerating is because the velocity is staying the same. It's not moving up and it's not getting slower. You have cruise control on and you're driving in a straight line, meaning that you're not changing your direction. But, there's a but, there's a lot of buts in physics, but if you have cruise control on and all of a sudden there's something in the way and you have to turn the steering wheel to the right or to the left, and you turn that steering wheel to the right or to the left, doesn't matter. Now you change your direction even though the cruise control is still on and you're traveling at the same speed, but you change your direction, then yes, you are accelerating even though you're not speeding up and you're not slowing down. How can you be accelerating in physics? Because your direction changed. Okay, so that's important to know. Now we've got a few more things to look at so we can talk about acceleration, because it really does get confusing here. Let's look at the next one. It says we've got 3 data charts. I'm going to call this chart 1, chart 2, and chart 3. And on those data charts it says here, describe the acceleration of each of the following objects. Well, let's look. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. What's going on with the time? The time is continuously increasing by 1 second. Okay? Now let's look at the velocities. From here to here, it increased by 1. From here to here, it increased by 3. The difference between 4 take away 1 is 3. 5 take away 4 is it increased by 1. And from here to here, it increased by 2. So look, 1, 3, 1, 2. What is this object doing? It's accelerating. It's changing its velocity differently. It's not a continuous speed the whole time. It's kind of like when you're driving and there's somebody in front of you and then you're able to they moved out of your way so you can speed up a little bit more, but then there's another car in front of you, so you kind of had to let go of the gas pedal, right? And you just kind of cruise a little bit and then they move and then you can hit the gas a little bit. That's what's going on here. You're continuously driving and you're able to hit the gas pedal and then let off the gas pedal. Hit it and let off. Okay? Let's look at the second one. Time is continuously going by 1. It increases. But look, from 0 to 4, there's a increase of 4. From 4 to 8, it changed again by 4. 8 to 12, it changed by 4. And 12 to 16, changed by 4. Is it increasing the velocity? Yes, it is. By how much? 4 every single time. So if it's continuously increasing velocity, then we call this a constant acceleration. Yes, my object is accelerating. Now the last one, time is increasing, and then let's look at the velocity. That's like the speedometer on your car. It just says 2, 2, 2, 2, 2. So what happens with the change here? No change. No change. No change. There is no change that's occurring. It's kind of like having that speed control on, that cruise control. So is my object accelerating over here? No acceleration. Is it moving? Yes. I'm going to put right here, yes, it's moving at a constant velocity. It is moving, so it has a velocity number, but mathematically, if we were going to do this math, acceleration value would actually be a 0. But a 0 does not mean that an object's not moving, okay? So we need to make sure that we know that, because we use the number or the value 0 often in physics, but it doesn't mean like 0. So let's keep going. We have another equation to write down, another formula. My formula over here is acceleration equals final velocity minus initial velocity over time. Let me say it again. Acceleration is final velocity minus initial velocity divided by the amount of time. Let me go ahead and write it with the abbreviations. Lowercase a equals capital V sub f minus V sub I over lowercase t. Sometimes you'll see it as a delta t. Okay? Sometimes you'll see it as an A equals delta at V divided by delta t. Okay? The lowercase letter a is a symbol for acceleration. The V sub f is a final velocity. V sub I is initial velocity. And delta t stands for time. We use meters per second square as our acceleration units in this class. That is going to be our SI units. Now, meters per second square can also be written as meters per second per second. That's where the square comes in. If I wanted to write this out, the meters per second square, that would be a meters slash seconds, and it's a squared second. So that means that there's 2 seconds, and that's where they get the square, or the seconds per seconds. There's 2 seconds in that square. Sometimes you might see it in kilometers per hour for every second that's occurring, or miles per hour per second. Those are all good, valid